node 1 will send a message to all its neighbors. Okay, so 3 messages sent in this example. And then at the end of round 1, all the nodes that receive a message know that they are at distance 1 from node 1. So they update their distance. They know that they are distance 1. Then at the second round, all the nodes at distance 1 will send a message to their neighbors. And then all the nodes that receive for the first time a message at round 2 know that they are distance 2 from node 1. Okay, so they can update their knowledge, and in this case, so after 2 rounds, node 6 knows that it is at round 2, at distance 2 from node 1. So for this very simple example, the problem can be solved in 2 rounds of communication. Okay, so I presented the model here, and I mentioned that you can send at each round 1 message, but there is a very important parameter, which is the size of the message. Okay, what is the size of the message you are allowed to send between any 2 nodes at each round? And there are 2 possible definitions, or 2 main definitions. The first definition is where you assume that its message is extremely short, say 1 bit. This gives a model called the congest model. Why? Because there are a lot of congestions if you have only short message. And the second model is when there is absolutely no restriction on the size of the message. Okay, this gives a model called the local model. And you may think that the second model, the local model, is a bit artificial, but actually it's probably if you compare the 2 models, there are, I think, more research on the local model than the congest model, because for many applications, communication is very fast, especially classical communication is fast and cheap. So the bottleneck for many computational tasks is the number of rounds needed to reach the conclusion. So the local model is probably the most important model in the distributed computing. Okay, and now quantum version of this. So I will give a more formal definition of quantum distributed computing in a few minutes, but for now I will simply say it in 1 word. The quantum version of distributed computing is the same as the classical version I just described, except that now we can send qubits instead of bits. Okay? And typically we assume that there is no prior entanglement. So the only difference is that now the messages are quantum messages. So the edges are quantum channels, and you can send quantum messages instead of classical messages. And again, there are 2 variants, 2 possible models: the quantum congest model, where each message is very short, say 1 qubit, and the local model, where there is absolutely no restriction on the size of each quantum message. Okay. So now the congest model. The congest model is very related to communication complexity. Why? Because we assume that its message is short. Each message consists only of 1 bit, or 1 qubit in the quantum case, which means that the total communication is somehow related to the number of rounds. It's not a direct relation, but there is some connection between the 2. So there is strong connection between the round complexity in the congest model and communication complexity. And using this connection, it has been shown that you can have a quantum advantage, typically polynomial speedup, for many important problems. The local model, on the other hand, there is no direct relation with communication complexity, and there are extremely few results investigating the power of quantum algorithm in that local model. And today, this talk will focus on this local model. Okay, so now I will give more details about this local model. So first, classical, say, deterministic algorithm. So when we consider a network represented by a graph, in most cases, especially in all the cases discussed in today's talk, the graph will be bounded degree, which means that in the graph, each node has a degree upper bounded by a constant. And the nodes do not receive any input, except, of course, their IDs. And we want to solve a problem related to the whole graph. A typical problem that will appear many times in this talk is computing a graph coloring. Okay, so let's see an example of how a classical deterministic algorithm works. So initially, as I mentioned, you don't have any knowledge of the topology of the graph, which means that the nodes only know their own ID. And then after round 1, what they can learn is the IDs of their neighbors. And after 2 rounds, they can get the IDs of the neighbors of their neighbors. And after 3 rounds, they can get all the IDs in a 3-hop neighborhood around them. Okay? And it's easy to see that at least in the classical deterministic case, this is the optimal strategy. Without loss of generality, you can always assume that the algorithm, an algorithm working in R round, will gather all information about its R-hop neighborhood, and that computes their output based on this knowledge. Okay, so what does it mean? This means that for classical deterministic algorithm, there is a very nice characterization of the round complexity, the number of communication rounds needed to solve a problem. The number of communication rounds is exactly equal to how far do you need to see in order to solve the problem. And with this nice characterization, it's possible to derive tight bounds on the classical complexity of many computational problems. And I will mention one of the main problems. It's probably the most important problem in the whole theory of classical distributed algorithm, especially in the local model. It's a 3-color ring on rings. So your network is a ring or cycle. And of course, we know that any ring has a 3-color ring. So for example, here, so a 3-color ring means a node color ring where neighbors have distinct colors. You see here, in this example, the ring is colored in 3 colors. And if you take any node and any 2 neighbors, the 2 neighbors are different colors. Okay, so it's a 3-color. And a seminal result in quantum distributed computing says that in the deterministic local model, a 3-coloring of a ring can be computed in log star n rounds. So what is log star? Log star is defined as the following function. It's the number of times you need to apply the log function before the result is less or equal to 1. But the definition is not very important. The point is that it is an extremely slowly growing function, much slower than log n, much slower log n, much slower log n. It's extremely small. And if you take, for example, this very big number, 2 to the power 65536, and the log star of it, it's 5. Okay, so it's extremely slowly growing. It's not a constant function, but very close to constant. Okay. So you can do it in log star n. And you may wonder why I'm not talking about 2-coloring, because a ring, at least when n is even, has a 2-color ring. You can color the ring in 2 colors. But the issue is that coloring a ring in with 2 colors is extremely hard. It requires a linear number of rounds in the deterministic setting. So it's not an interesting problem because we don't have any clever solution for that. That's why essentially all the theory of coloring for cycle focus on the 3-coloring version. Okay. So now I would like to give more details about the quantum version. But before that, is there any questions about what I've said so far? Okay. Yes.
So the reason the 230 is order n is because 1/2, but the first one decide which color is it and then have to tell everyone else which.
Yes, yes. If the proof is not extremely difficult, but it's the same intuition. So once somebody fixes something, everybody should be coherent and follow the same ordering. And you cannot do it without global communication. While for three, it's not the case. I mean, even if one fixes, there's a lot of degree of freedom for the others. Yes, so if you want to prove a lower bound, this is exactly the argument you mentioned. It's a few lines. Exactly. Anything else? Okay. So now, quantum algorithms in the local model. So again, the local model is like the classical, the quantum version of the local model is like the classical version, but you can send one quantum message instead of a classical message. And again, we are talking about the local model. So this means that the size of the message is unbounded. So in this example, it's a path of 4 nodes. Okay, so at each round, each adjacent nodes can send one message. We can represent a quantum distributed algorithm using quantum circuits. And sometimes it's useful to prove things. So here, I'm trying to do it for first with 0 round. So 0 round is easy. There is no communication at all. Since we assume that there is no prior entanglement, the only thing that the player can do is apply a local unitary and measure. Very simple strategy. So now, if you have 1 round of communication, the circuit will be something like that, where the box here represents this thing, represents the exchange of registers. Okay? So yeah, each node apply a unitary, then they exchange the registers, the communication step, and then the node measure what they received with their private registers. And if it is 2 round, you will have 1 more step of layer of communication, and 3 round, you will have 1 more layer of local communication, 1 more layer of local computation. Okay, so you can represent a quantum distributed algorithm, including the communication as a circuit. And sometimes it's easier to prove things or understand the properties of quantum algorithms. Okay, and of course, the main question we would like to understand is whether there is a problem for which we can show a distributed quantum advantage. Okay, so we would like to understand whether quantum algorithm can be more powerful than classical algorithm in this model. And fortunately, the answer is yes. We know this. So this has been proved with Harumichi and one postdoc on Sis-Holzmanis a few years ago. We know that there is a computational problem that can be solved quantumly in a constant number of rounds, but classically, you need a linear number of rounds. So you have a huge gap between classical and quantum here. And this separation improves the previous separation, which was 1 versus constant, 1 versus 2. You know, it's a constant versus linear. It's a very huge separation. So what is the problem we considered? The problem is sampling from the outcome of a quantum circuit that measures a graph state in a random basis. The point is that in constant round, a quantum algorithm can construct the graph state of corresponding to all the network, all the graph. And then each node can locally measure it in a random basis and output the outcome. Okay, so it can be done very easily in the quantum setting. And we can show that this problem is very hard for classical algorithm. You need a linear amount of round if you want to simulate this process and sample from the same distribution. But you have 2 significant weaknesses for this result. The first is that the computational task considered is not useful. I mean, sampling from the outcome of a random circuit is not useful. You will never use it in real life. And the second thing, it's more subtle, but The point is that the solutions are not efficiently checkable. Okay, checking if a sample is really a sample from the description we want to sample from is hard. And we can show that if you really want to check whether your output is a real sample, you need a linear amount of rounds, even in the quantum setting. So we can sample, but checking that if the sampling is good, so checking if there is a quantum advantage requires a linear amount of rounds. And these two weaknesses are very similar to the several papers on quantum supremacy for quantum circuits. So there are a lot of papers showing that quantum algorithms can be faster than, more powerful than classical algorithms. Even very weak quantum circuits, shallow quantum circuits that can be realized in the lab. But for all these papers, they have the same problems. It's for an artificial task, and this quantum superiority cannot be verified efficiently. So we have the same issues appearing here. So the main question we would like to really understand is whether we can have a quantum advantage for a problem that someone actually cares about. Not an artificial problem, but a really interesting problem. This is the first question. And the second question is whether we can show a quantum advantage for a problem that can be checked efficiently. And I will come back to that in a few seconds. And the conclusion is that nobody really knows. I will go back now to this three coloring. Remember the problem I mentioned, three coloring. So classically, we can do it in log star n rounds. Very efficient, but not constant. So a fundamental question is whether quantum help. Okay, it would be wonderful if quantum can solve it faster. But as I said, log star is very, very low, very slowly growing. So faster will maybe say constant round. So can we do constant round in the quantum setting? It's a very fundamental question. A lot of people considered it. Actually, it was already mentioned in very early papers on quantum distributed computing as an open problem, but nobody really knows the solution. It's probably the most intriguing quantum question, the open question. Okay. So now I would like to notice that essentially all problems studied in the literature of distributed computing, especially in the local model, have the same property as three coloring. They are locally checkable. It's easy to check if a solution is really a solution in a constant number of rounds. And I'm going back here because I didn't mention this, but this is the case for coloring, because coloring can be checked extremely efficiently. In order to check if a coloring is really a coloring, or really a three coloring, each node need only to check if its color is distinct from the color of the two neighbors. And this can be done in one round by exchanging your color with the color of the neighbors. So if the candidate is not a coloring, then at least one node will be able to detect it. And this requires only one round of communication. So it's extremely easy to check the solution here. And as I just said, it's the same for many, many important problems in distributed computing. So the formal question we would like to understand is whether there is a problem that is locally checkable, exactly the same condition, for which we can show a quantum advantage. And this is really the most important question in the field. And I have talked with many experts in both quantum computing, classical distributed computing, and so on. And the natural conjecture seems to be that for all those locally checkable problems, there is no quantum advantage. This is a natural conjecture. And the goal of this work is to make progress on this conjecture. Okay, and in order to make progress, we use the concept of causality. Okay, so I think most of you know this, but the point is that quantum mechanics should satisfy causality. And what does it mean for quantum distributed algorithm. This means that, for example, if you look at this node here, this node, this one, the output of the bottom nodes of the path. We know that this output depends, the outcome of this output should only depend on the input within the light cone of the computation. Why? Because this measurement is on this wire. This wire comes from here, this comes from here, this comes from here. So this thing has no impact here. So you can see that with such light cone arguments, which follows from causality, you can give some relation between the input and the output of the quantum series. And the next step is to go further and define a whole concept of non-signaling algorithm. What we want to do is to define a model so that can be done, that can do anything except violating causality. Okay? And this has been done in prior works. And the name for this is a notion of R-hop non-signaling distribution. I will try to give a definition here. The definition is that for any set of node X, so in this picture, the nodes in orange, if you consider the blue nodes, that is the nodes which are at distance at least R from the orange nodes, then changes in the output of the blue nodes should have no influence on the output distribution of the orange nodes. Okay? And any probability distribution on the output that satisfies this condition is called the R-hop non-signaling distribution. So it's not really algorithm, it's distribution. We are talking about probability distribution on the output. Okay, so we have now three models. We have classical, we have quantum, and we have non-signal algorithm in this order. So quantum can simulate trivially classical, and non-signaling algorithm are stronger than quantum because quantum needs to satisfy causality. And we don't understand at all the power of quantum distributed algorithm. This is what we want to solve, to understand better. In particular, we would like to understand whether this conjecture is true or not. And the first point is that classical algorithm, especially deterministic, classical deterministic algorithm, we understand them very well. Why? Because again, as I explained at the beginning of the talk, we have a very nice characterization. The number of rounds of a classical algorithm is needed to solve a problem is equal to how far you need to see in the network in order to solve the problem. So we have many, many tight bounds for classical distributed algorithm because we have a very good understanding of that notion. Non-signaling distribution, it's essentially probability theory, classical probability theory. We have to understand the properties of a probability distribution satisfying solving the problems. So we know very well the classical case and the non-signaling case. So this leads to a natural approach to prove the conjecture. The approach is to try to show that for any locally checkable problem, non-signaling algorithms are not more powerful than classical algorithms. Because if you can show that non-signaling equal classical, then everything collapses. And we obtain classical equal quantum equal non-signaling. Because quantum is sandwiched between classical and non-signaling. Okay? And our main result is, well, before mentioning, I will just briefly describe some prior work related to that. There are very few prior work, but there are essentially two that prove this thing for special problems. So for example, it was proved very easily that for two coloring rings, classical and quantum and non-signaling collapse. This is exactly from the argument you mentioned. From two coloring, it's extremely hard because you need some collaboration between all the nodes. Okay, so you cannot solve it classically, but you cannot also solve it quantumly, and you cannot solve it with a non-signaling algorithm either. There is another one, very recent, that showed also that quantum does not help for arbitrary bipartite graph, or coloring arbitrary bipartite graphs. It was presented last week at TQC. But in order to prove the conjecture, we need to show that quantum does not help. And more precisely, we would like to show that non-signaling is not more powerful than classical for any problem, any locally checkable problem. And this is very challenging. Proving this for specific problem can be done, but we have to prove it for any locally checkable. And our main result shows that this natural approach doesn't work because there exist many classes of locally checkable problems for which non-signaling algorithms are more powerful than classical algorithms. Okay. Again, so our goal is to show that non-signaling does not help. Non-signaling equals classical for all the locally checkable problems. We had a few results in that direction, but we show that actually this is not the case because there are many problems for which we have an advantage using non-signaling algorithms. So a positive interpretation of this is that there might be a quantum advantage. But of course, the theorem does not say anything in that direction because this result talks only about non-signaling algorithms. Okay, so are there any questions up to this point? Okay, so now I'll finish with a few slightly more technical slides. So first, if you look at the paper, there is a figure that mentions all the problems, all the models considered. And there are a lot of models, so many things. That's why we have 10 authors. So each author contributes to one model and so on. So it's very a big web of models. But in this talk, I mentioned only the model related to quantum. And there are mainly three of them. The classical one, so randomized, the quantum, and the non-signal. And our main result states that for any locally checkable problem, if you can solve it in a smaller of log n rounds, classically, so in the deterministic model, then you can solve it in constant rounds in the non-signaling model. Okay, and this gives you immediately one very interesting consequence. Remember that for three coloring rings, classically, you can do it in log star n. Log star n is a big O of log n. So from this theorem, you get immediately a non-signaling algorithm with constant complexity. But this one is actually not new. It was suggested by some mathematician people doing graph theory, obtained results that suggested something like this. But our result works not only for three coloring, but also for any locally checkable problem. So their result was only for three coloring, and this theorem holds for any locally checkable problem. So a much more general statement. Okay, and again, this shows that the natural approach that I mentioned in the previous slide doesn't work for a very large class of problems. Okay, and the positive interpretation is that there might be a quantum advantage. The second result is about trees. The prior result was about any possible graph. here, the new one is only about trees. So trees are graphs of this form. And in trees, we show that any locally checkable problem that can be solved in the small O of log n rounds in the non-signaling model has actually a very efficient classical strategy, log star n here. And what does it mean? This means that for trees, there is no locally checkable problem with locality between, right, in this region, the middle region here, so between log star and log n. Why? Because if there is a problem with locality in that region, the red region here, then we can apply the theorem and obtain a classical algorithm with complexity log star. So we will be on the left region here. So this really shows that there is nothing in the red region mentioned here. So we get a better understanding of the complexity of quantum distributed algorithm using this. Okay, and I will spend the last 3-4 minutes describing some idea about the proof of the main result. So remember the theorem, the main result is this. So if you can solve a problem in small O log n rounds classically, you can solve the problem with a constant number of rounds in the non-signaling. And we use two tools. The first one is a constant round non-signaling strategy for three-coloring a graph. This is, as I mentioned in the previous slide, from 2 papers from mathematicians. The second tool is a reduction. It's adapted from prior work. It's not very difficult. It follows easily from prior work. From any locally checkable problem that can be solved in a small O log n rounds in the deterministic local model to a new problem, which is a problem of computing a coloring of a graph with d plus 1 colors, where d is the maximum degree of the graph. And when you have this, you can give the proof. It's a little bit technical, but the sketch is like this. You first extend the strategy from tool 1. So tool 1 is for ring, and you can extend it to obtain a constant round non-signaling strategy for coloring a pseudo-forest. So pseudo-forest is a generalization of a tree in graph theory. You can do it. Then you can observe that if you have a bounded degree graph, you can decompose it into pseudo-forest. Then you show how to combine 1 and 2 to get a d plus 1 coloring for any graph of maximum degree d. And then you apply the second tool and you reach the conclusion. Okay, so it's fairly, there are a lot of technical details, but the most interesting part, I think, is a tool 1 from this prior work. And I will finish by using one slide to describe this very, very nice, very interesting constant round strategy for coloring a ring. Okay, so we have a ring here, and we want to compute a 3-color ring. So what is the strategy described in those 2 papers? It's a probabilistic process. You first put a random color. We have 3 choices. A random color as a random position. For example, I put a 2 there. Then I put another color, another random color as another random position. So for example, here, blue there. And then I will repeat many times the following process. You pick a random position, okay? And you color it with the color distinct from the color of your 2 neighbors, 2-color neighbors. So around here, I have, sorry, I have, here. Okay, sorry, yes, I found this. Okay, so here I'm taking this. As color, I have this and this. So I choose another color, which will be green. And I continue like that. I choose this one. And as color, I have I have only the orange, so I choose orange. Then I choose another one, so for example, this one, and I blue. The only solution is blue because around there is green and orange. And I continue like this. This one will be orange, and so on. And if you do this, what you will obtain, it's trivial to see, is that you obtain a valid tree coloring. But what it's the process is producing is a probability distribution over all valid tree coloring of a ring. But what is non-trivial to show is the following thing. The restrictions to any two sets of variables, two sets of vertices at distance larger than 2 are independent of each other. So for example, here, if you consider the set of red nodes and the set of blue nodes, the distance between the two sets is larger than 2. So the theorem says that the marginal distribution of the whole distribution should be independent. And what does it imply? It implies that this probability distribution is a one-hop non-signaling distribution, which is exactly what we wanted. So you get constant round, and actually the number of rounds is 1. It's extremely efficient. It's very surprising. I mean, this is a natural process, but proving this theorem is non-trivial. Okay, so I will finish now. So we have shown several relations between classical quantum non-signaling local models. The main message is that for a large class of problems, it's not possible to exclude quantum advantage by using non-signaling arguments. Okay, a positive interpretation of this is that there might be a quantum advantage. Open problem. So first is to prove such a quantum advantage for locally checkable problems. The next one is to try to exclude quantum advantage for concrete problems. So for example, tree coloring. Can we show that quantumly you really need log star like the classical setting? And the last one is whether shared entanglement can help. Okay, if you compare quantum without shared entanglement and quantum with shared entanglement, does the later is the later more powerful than the former? Okay, so I will stop here. Thank you for your attention.
Thank you very much. So are there any questions, comments?
Sorry, could you give me that definition of locally checkable model?
Are there any questions, comments?
Sorry, I didn't hear well. So
I could not understand the definition. So locally checkable. So what is the definition of locally checkable?
Yes. Locally checkable means it's probably better to see the example. Okay, so for this tree coloring, the probability is that the nodes can check if you have a solution or not by looking at their neighbor. Okay, so for a coloring, a node can check if it is really a tree coloring or not by looking at the color of their neighbors. This is the definition of locally checkable.
Oh, okay. So there is some concept locally testable and checkable completely same. Locally testable something.
Yes, locally. Yes, the same, yes.
Recently, some people work on the locally testable code.
Yes, so it's not exactly the same. I mean, locally checkable code, it's not the same concept. It's probably similar, but here locally, I mean, you have a network and each node can check by communicating with its neighbor, really the neighbor. So it's a concept of locality in distributed computing. So it's not completely related to this locally checkable error correcting code.
Slightly different.
It's different because the model is different, yes.
Oh.
Distributed computing.
Of course, this is code. Error correct word means that only the one decoder make a decoding. But when they made some decoding, something like that decode can be constructed by combination of the local calculation, local operation.
Yeah, of course, the inspiration is probably the same in error correction. I mean, you want to have a code which is locally checkable. This means by looking only at a few positions, you are able to check if something happened or not, if you are in a code word or not. But here, really, everything should be with neighbors. The most important property is that you have to look at the neighbor. It's not only a small number of positions, the position should be very close. It should be the node and its neighbors.
Okay, I understand.
Okay.
Other questions, comments? Yeah.
So does the adaptive property help? One major local operation. Scale non-signal. Maybe better than the deterministic local quantum model.
We don't know. So we know that, as I mentioned here, if you don't care about the problem being locally checkable, then there are a lot of things that you can do in the quantum setting. You can generate distribution which cannot be generated classically. So it's very easy. But when you really want to consider a locally checkable problem, we don't have any example where there is a quantum advantage. And the classical case, the strategy is, as mentioned, very easy. You don't have any clever algorithm. You simply gather all the information about your neighborhood, and then you make your decision. So quantumly, we would expect that you can do something more powerful, but we don't have any such example for a locally checkable problem. And the conjecture is that it cannot exist. But I'm not sure. It's a very new field. So the conjecture, I'm not sure if everybody agrees with this conjecture.
Other questions?
Yes.
Is there any difference between locally checkable and its quantum version, quantum locally checkable?
I'm not sure. I would say no, because we are in the local models, so we don't care about the size of the message. So intuitively, I would say no. But of course, we can use some entanglement and some clever things. So I'm not sure it's a straightforward, there's a straightforward proof that this does not make a difference. But at least we don't know, I don't think we know any example where there is a difference between classically locally checkable and quantum locally checkable in the local model. It's a good question. Yes, it would be nice to investigate that.
So, other questions, comments? Okay. If not, let's thank the speaker again. Let's thank the speaker again. So the next speaker is Shen-Wan. Are you online?
Yes, I'm here.
So could you please share your slides?
I friends likes to sharing, so it seems that I cannot share it now. Oh, thank you.
Yes, okay. Now we can see your slides.
Okay.
So in a few minutes. Okay. Now we can see your slide. So in a few minutes.
So I
Okay.
think it's 10. So
Now the second speaker is question 1 from the University of Edinburgh. The title is Time Efficient Quantum Entropy Estimator via Samplizer. Okay, so please start.
thank you, Kano Sensei. This work is mainly done when I was at Nagoya University, and I'm now working at the University of Edinburgh. And this work was joined with Zhichen Zhang from the University of Technology, Sydney. And thank you very much for inviting me to present my work in Shenzhen-Nagoya workshop on quantum science in 2024. And this talk is based on our prior work in ESA 2024. To begin with, let us introduce entropy. For probability distribution P, we know there are Shannon entropy and Delaney entropy. We can naturally generalize to the quantum case, and they become von Neumann entropy and quantum Delaney entropy. In the classical world, we know they're efficient estimators. For Shannon entropy, we know that the sample complexity is n over log n, and n is the dimension. Also, we have alpha Delaney entropy estimator. All of these estimators have time complexity linear in the sample complexity. In the quantum world, we have two models. One is sample access and the other is query access. For sample access, given access to identical copies of the quantum state. And for query access, it is given access to the state preparation circuit of the quantum state. And in this work, we mainly focus on sample complexity. For von Neumann entropy estimator, prior work showed that its sample complexity is O(n) squared, and it can be estimated in time complexity n to the 6. Similarly, for quantum alpha Delaney entropy, we can also estimate them. Well, for the completeness, we also introduced the result about query access model. For von Neumann entropy estimator, we know that the query access, query complexities tilde O(n), and also we have their query complexity for alpha landing entropy. The motivation of this work is that there is a cubic gap between the sample complexity and the time complexity of the non-quantum entropy estimators with sample access. As can be shown here, the blue part is the prior best time complexity. The sample complexity and the time complexity. And our question is, can we estimate quantum entropy with time complexity linear in the sample complexity? Is the prior best time complexity. Our main result is that we propose new quantum entropy estimators based on an algorithmic tool samplizer. As shown in the following table, especially for alpha equals 1, which means von Neumann entropy, we propose a quantum entropy estimator with sample complexity tilde O n squared while retaining the almost same time complexity compared to the prior work by AISW20. Their time complexity is n to the 6th. Thus, we obtain a cubic improvement in the time complexity compared to the prior work by AISW20. Our idea can be described in one sentence, that is, design quantum sample access algorithms by imitating quantum query access algorithms. The intuition is that quantum query access algorithms usually have time complexity linear to the query complexity. Now let us consider a simple quantum query algorithm for estimating von Neumann entropy, which is based on quantum singular value transformation. The key step is given a unitary operator U whose upper left corner is a quantum state rho, and we can do QSVT to transform it to a unitary operator U prime, whose upper left corner is minus log rho. Then we can apply the Hadamard test. Then we can estimate the von Neumann entropy by repeating the Hadamard test. So the quantum circuit is simple and can be visualized in this figure. Then we can estimate the von Neumann entropy. Then our idea is to samplize this circuit. The quantum circuit can be simple and can be visualized. Now we introduce the samplizer that can samplize a quantum query algorithm to a quantum sample algorithm, such that the two algorithms have similar behavior. Now we introduce the samplizer. For quantum query algorithm, we assume that it has access to quantum oracle U, and it's described by a quantum circuit family CU. For each UI, it's either controlled U or controlled U dagger, and GI are quantum gates that do not depend on U. And here Q is the query complexity. There are many examples in the literature. And for quantum sample algorithms, it is given access to independent samples of a quantum state rho, which is described by a quantum channel family, E rho, and as shown it is in this figure. Here, rho tensor K is considered to be the input of the whole sample algorithm, and K is the sample complexity. And there are also many examples in the literature that in this input model. Having introducing quantum query algorithm and quantum sample algorithm, we define the sampleizer here formally. A sampleizer is a converter from a quantum query algorithm to a quantum sample algorithm with the following property. For the precision delta and quantum query algorithm C with oracle U and quantum state rho, there exists a unitary operator U rho whose upper left corner is rho, such that the sampleized version of C with input rho is very close to the quantum query algorithm C with oracle U rho. And that's why we call them have similar behavior. And here, this is the diagonal. So our tool is that there is a sampleizer such that for any quantum query algorithm C with query complexity Q, the sampleized version can be implemented using sample complexity to the theta Q square over delta. That is, for quantum query algorithm C with query complexity Q, after the sampleizer, we can obtain a quantum sample algorithm sampleize delta C and its sample complexity Q square over delta. So, having obtained such sampleizer, let's recall the simple quantum query algorithm for von Neumann entropy estimator. So using the sampleizer, we just sampleize the middle part while remaining the rest. And then this sampleized version have similar behavior of the quantum query algorithm. And then we can repeat this circuit many times in order to ensure the error. Anyway, the detail can be complicated, but the idea is simple. So after the complicated error analysis, we can show that the von Neumann entropy can be estimated to precision epsilon with sample and time complexity n square over epsilon to the 5. Moreover, inspired by the quantum query algorithm for estimating the alpha Zerani entropy of probability distributions, we further have the estimators for quantum alpha Zerani entropy. And it is noted that the sample and time complexity are almost the same, only up to polylogarithmic vectors. So at the last, we explain how the sampleizer is implemented. So for the first step, we require the density matrix exponentiation. That is, we can implement a quantum channel E such that E is very close to the Hamiltonian simulation-like unitary operator, E to the minus I rho T, and rho is a quantum state. This channel can be done using T square over delta samples of rho. And then we can do quantum singular value transformation on the Hamiltonian simulation-like unitary operator. By implementing the logarithm of unitaries, we can transform e to the minus I rho to a new unitary operator with upper left corner rho. And this is already pointed out in prior work, and they show that such quantum channel E can be implemented by using 1 over delta samples of rho. And the last, we generalize the sample to query lifting theorem, and we have the following construction. For each unitary operator Ui in the quantum query algorithm, we can replace each Ui, U1, U2 to UQ by a quantum channel. Say Ui is replaced by a quantum channel EI, and with input state rho tensor S. And here S is roughly Q over delta. And there are in total Q such replacement. So this requires Q square over delta samples of rho. And this makes us able to implement the sampleizer. Also, we can show that the implementation of the sampleizer is optimal only up to polylogarithmic factors by combining two prior results, which is the sample lower bound for sample-based Hamiltonian simulation, and the optimal quantum query algorithm for Hamiltonian simulation. And we can show that any sampleizer requires the sample complexity omega Q square over delta. And we raise some open questions that may be of broader interest. The first is that the sample complexity of the sampleizer is shown to be tilde theta and Q square over delta. A direct question is that can we make it tighter and improving the logarithmic factors? The sampleizer is shown to be tilde theta Q square over delta. And also, all of the existing quantum estimators for von Neumann entropy have sample complexity tilde O n square, while the best non-sample lower bound is only omega n. This is a quadratic gap, and the lower bound is suggested by prior work. So a problem is, can we show a matching lower bound for the von Neumann entropy estimator, which I believe should be omega n square. And the last, can we obtain new quantum sample algorithms for other problems of interest through the sampleizer? So thanks a lot for your attention.
Thank you very much for your talk.
Thank you.
So the now session is open to questions and comments.
Sorry, I have one question. So could you show me the query, form of query? So this is depend on the row.
Do you mean here?
Query. This is not you previously like log row. Query. Yes. So somehow looks. I feel that this query is not so natural. Why you consider this query?
This query algorithm is is an easy one to estimate the von Neumann entropy in the query access model. And the query access model assumes that we have state preparation circuit to prepare rho, the purification of rho. So once we have the state preparation circuit of rho, we can prepare rho. And also we have a way to implement the minus log rho upper left corner unitary operator by queries to the state preparation circuit of rho. So once we have state preparation circuit of rho, we can obtain the two.
I cannot understand. Once we could prepare density matrix, state of the density matrix rho, then you can make this unitary.
This means that if you can prepare rho, then you can using the way you prepare the unitary operator, you prepare rho to implement this operator.
This is unitary, I think. This is unitary matrix.
Yeah, this is a unitary.
I'm very confused. So why you can make this unitary from density matrix rho? How did you make log rho? And other part it should be some.
So for the eigenvalue that is very close to 0, then there is a cut. So for two large things, we just ignore.
I cannot understand how can you make that unitary? You can take logarithm. Of course, mathematically this is possible. But what physical operation can realize that operation?
Okay, in detail, the transformation is given in here, line 1 to line 5. And we approximate the logarithm function here by px. And here, there is a parameter delta p. For x in delta p to 1, px is close to a logarithm function. However, when x is, say, less than delta p, then we do not hope px to approximate log. So in this sense, actually we are implementing p rho, but not minus log rho.
Still, I could not understand. You write down some operation to make unitary satisfying that condition.
Which condition do you mean?
Because the unitary has that form log rho on that diagonal block.
Do you mean this one?
Yes. But initially also I'm confused. This is unitary rho, star. This is different from the generation of density matrix rho.
Yeah. This is different from the definition of the data preparation circuit of rho. But we can, once you have a state preparation of rho, you can implement such U, whose upper left corner is rho.
This is true. This is you have some probabilistic procedure to make U from the state rho, I think. Or if you perfectly generate with probability 1, so then it is enough to that simply complete the same as the sample complexity. If you can make that unitary from density matrix law with probability 1, so then your setting can be reduced to the sample complexity. Not
This
complexity.
can be made deterministically.
So then this means that that operation can be reduced to the sample complexity. Because you can generate the density matrix law, then you can make that conversion operation. So then you can make that estimation. So in that case, this means that that process can be considered a part of the sample complexity.
I'm sorry, I didn't get you very clearly.
Because if you generate that kind of unitary from density matrix with probability 1, so then you can, so then that problem reduced to the sample complexity. Because if you have n copy of density matrix law, then you can make unitary operation of n copy. So then the operation of the query complexity can be implemented with operation as a sample complexity. A query complexity and sample complexity, yeah, sample complexity.
Oh, the query complexity here means that the number of queries to the state preparation circuit, but not the U here. So in this sense, it seems that there is no way to implement the state preparation circuit by samples overall.
This means that you cannot convert with probability 1.
I don't think so. I think here
If you can convert, this
the-
means that the operation can be simulated with sample case.
the implementation are all deterministic, so the only probability comes from the measurement here.
Oh, excuse me. Could you continue the discussion personally? Okay. Other questions?
The only probability comes from the measurement here.
Oh, excuse me. Could you continue the discussion personally? Oh, no? So let's thank the speaker again. Thank you very much.
Thank you very much.
So 5 minutes break. So let's thank the speaker again. Thank you very much. Break. Hello, Haydon. Can you share your slides?
Okay. Yeah. Can you see the
Yes,
slides?
in full screen, please. Oh. Yes, thank you. Yes, in full screen, please. So let us resume the session. The next speaker is Haidong Yuan from Chinese University of Hong Kong. He tells us about incomplementariety in multiple matter quantum methodology. So please start.
Thank you. And thanks for the invitations, especially Masahito Hayashi. So I'm going to talk about the incompatibility in multi-parameter quantum metrologies. But first, I'm going to give a brief introduction about quantum metrologies, and then talk about two incompatibility issues. So the measurement incompatibility and the probe state incompatibilities. Right. So the general procedures, quantum metrologies or the quantum parameter estimations, is to estimating some unknown parameters within some quantum dynamics or in general in some quantum channels. So to estimating these parameters, the general procedures is you first need to prepare some initial states, low zero here, and then let it go through these quantum channels or the quantum dynamics. You get the final states. And then you pick a measurement. After this measurement, then you get a distribution of the measurement results. From this distribution of the measurement results, then you can make an estimations. This last step is typically solved by the maximum likelihood estimations, which in the asymptotic limit minimize the mean square errors when the estimate is unbiased. So the general goal of this quantum metrologies, one goal of the quantum metrologies is trying to minimizing this mean square errors. So here we are going to assuming these estimators kind of locally unbiased. So the locally the expectation of these estimators is going to be equal to the true values. On these conditions, we're trying to minimizing this mean squared errors. This problem in the single parameter case, or even in the classical case, the problem is well studied, and from the statistics or the classical camera bounds is that the minimum variance you can get is lower bounded by this quantity, these two quantities here. The one mu is the number of measurement repetitions, basically the number of data. And the classical FC is the classical Fisher emissions, meaning essentially just the informations you contained in one measurement. And this classical Fisher emissions can be computed in following formulas, right? But in the quantum case, you can multiple optimizations you can perform. And the first optimization you can perform is to optimize the choice of measurement. If you optimize the choice of measurement, then the classical camera band becomes a quantum camera band. And the only difference between the quantum camera band and the classical camera band is this, you're replacing this classical fishing machine with the quantum fishing machines. And the quantum fishing machine, as we just mentioned, is just the maximization of the classical fishing machine over all possible choices of measurement. And these optimizations have been solved and it can be computed exactly analytically from the final states and another quantity called the symmetrical logarithm operators. And this symmetrical logarithm operator can be analytically solved or in at least as a analytical procedures to solve it, which is just through these equations, right? And the important thing for quantum camera band is that for the estimation of single parameters, this is not only a lower bound, but actually a achievable lower bound. So this indeed give you the minimum values. Right? And the optimal measurement to achieve this lower bound is the project measurement on the eigenvectors of this LS, which is SLD, right? Intuitively, if you haven't learned the classical fishing machine or quantum fishing machine previously, then intuitively this fishing machine just characterize some distance between some neighboring distribution or neighboring states. So this is the procedures we just talked about. So you prepare some initial states, go through the quantum channels, get the final states, make a measurement to get the probability distributions. Now imagine this parameter is shifted a little bit, right? The parameter becomes theta plus d theta, where d theta is small quantities. Then the final states is also shifted a little bit, and the final probability distribution also shift a little bit. And the classical fishing machine just quantifies the distance between these neighboring distributions. And if we optimize the measurement, then the quantum fishing machine basically quantifies the distance between the neighboring quantum states. Of course, you can further optimize the probable states. Then you will get another layer of fishing machine, what's called quantum channel fishing machines. That quantifies the distance between the neighboring quantum channels. Right? So this is well started, and you can find some details in the recent reviews. And if you also including the different strategies, so if you have multiple choices of channels, you can put them in parallel or sequential or quantum switches. And then for any strategies, you can using one our programs, our SDP program, numerical programs, to find out the maximum quantum fishing machines, also as well as the optimal strategy to achieve it. Right? So for single parameter estimations, the optimal strategies, at least there's some systematic ways to find it. Of course, when the number of channels is large, the computation is probably not computable, is very costly, so you may not be able to carry out the optimization, but at least there's some systematic ways, procedures to tell you how to find out the optimal strategies. Right? For example, suppose you have a phase estimation, but with amplitude and damping noises. Suppose you're giving you two uses of these channels. then if you substitute these channels and into our program, then this will give output the optimal sequential strategies. Suppose you're choosing the sequential strategies, and this will give you the optimal gates, two gates, to give you the maximum precisions. Of course, these optimal gates are in general kind of complicated, but you can use it as a benchmark. If you're choosing other strategies, this can also give you output the maximum precisions or maximum quantum estimations. So this for single parameter estimations, I think that's relatively well good understandings on the maximum precisions you can achieve. But for multi-parameter quantum estimations, and the problem is much complicated and there's much less understandings. So let's first talk about the general quantities to characterize the multi-parameter quantum estimations. Now suppose you have multiple parameters where theta now is a vector instead of a scalar. So the quantification of the precisions now is given by the covariance matrix. And similarly, we have this classical camera bound and the quantum camera bound. These bounds are still valid in multiple parameter case, but in the multiple parameters, the classical bound is still achievable. You can still, like in the when mu is asymptotically large, you can still using the maximum likelihood under some regular conditions to achieve it. But in the quantum camera bound, is in general not achievable. The main issue is exactly the incompatibility issues, right? But we talk about this in the single parameter case to achieve the quantum fishing machines. The optimal measurement, one optimal measurement we chose is the SLDs. Basically, SLD is the optimal observables to achieve the quantum camera bound. But then when you have multiple parameters, each parameter you have a corresponding SLDs. And these SLDs in general will not be commutative with each other. So they are not compatible. And you cannot find a single measurement to simultaneously achieve this quantum camera bound for all these parameters. Right? So this is called measurement incompatibilities. Due to these incompatibilities, the quantum camera bound is in general not settleable. Since the quantum camera bound is not settleable in general due to these incompatibilities, so then we are going to take one step back, think about just using a single measurement just to approximate these multiple observables instead exactly implement these observables simultaneously, right? Now, using a single measurement, we can think about this general PLVMs just as some project measurement on some big space. Using this big project measurement on this big space, we can kind of constructing n commuting observables to approximating this n non-commuting observables. Right? Of course, there are some errors. If this original observers are not commuting with each other, then we cannot exactly this commuting observer cannot equal to this non-commuting observer simultaneously. So there will be some errors, and we are going to quantify these errors again using this sort of mean square errors. Right? These errors will naturally have some trade-offs among them. So if we're choosing to minimizing one errors, make it equal to zeros, then the other errors may increase. Right? And these errors are closely connected to the measurement uncertain relations. So the measurement uncertain relations is kind of different from this preparation uncertain relations in the textbook, which is the Lobson sitting uncertain relations in textbooks. This textbook uncertain relations basically is about impossibilities preparing some quantum states, which has sharp distributions for these two non-commuting observers simultaneously. This does not involve any measurement. For the uncertain relation, we are going to connect with this incompatibility issue with this measurement uncertain relations, which is kind of the first proposed by Ozawas, and then strengthened by Blanchard. So the type or the tight relation for two observers on pure states is given by these formulas. Right? The important quantity is the right-hand side, which is proportional, which is given by this trace norm of these quantities. Right? So if this quantity is non-zeros, then the errors, both errors cannot be simultaneous zeros. So there's some trade-off. And this trade-off relation or these uncertain relations is only for two observers, which is tight for pure states, but not tight for mixed states. Right. So we kind of generalize this uncertain relations to arbitrary number of observers, then apply it to this incompatibilities in quantum metrologies. But we are not going to go through these procedures. Basically, we are going to just tell you exactly just the results. Right. So after we generalize this uncertain relations and apply to the quantum metrologies, we find out that the trade-off relations can be quantified. We obtain this trade-off relations. Basically, it involves this two quantities, which is both the imaginary part of the quantum geometric tensor and the imaginary part of the quantum geometric tensors. Right. The real part of this quantum geometric tensor is just the quantum efficient matrix, and the imaginary part of the quantum geometric tensor, in the pure states case, is just proportional to the Bailey curvatures. So using these quantities, we can the trade-off relation we can obtain is these relations. So this quantity, which quantifies how close this classical efficient machine to the quantum efficient machines, is upbounded by these quantities, where this lambda q are the eigenvalues of this matrix. Right? So if all the lambda q are zeros, then all these are zeros, then the upper bound is n, which means that this basically this just identities, which means that classical efficient machine can equal to the quantum efficient machines. And if the classical efficient machine cannot achieve the quantum efficient machines, then this is some matrix is less than identities, and the trace will be less than n. And basically this lambda q basically quantifies the gap between the classical efficient machine matrix and the quantum efficient machine matrix. I should mention that Benthusuma also obtained some similar relations with these quantities, not exactly this quantity, but with FQ, FC inverse. But there's no analytical construction of the measurement. So this trade-off relation for pure states, this bound is tight. And then we give analytical constructions of the open measurement. to achieve this bound. I should mention the optimal measurement are not unique. This actually gives you some flexibilities in the practice to design suitable optimal measurement. Right? So I'm going to give two examples. So the first example is to measuring some parameters, basically to measure these three parameters, the gamma 1, theta 1, alpha 1 on the two quantum bits. These are just the angle of some rotations. Right? So R, Y is just rotation along the y-axis, and RZ is just rotation along the z-axis with some angles. So this, if we like substitute these states into our, you calculate the classical efficient machine, and you calculate the quantum efficient machine and the Bailey curvatures, then you can get the trade-off relations, right? So these are the upper bound you get. So this quantity is some quantity always smaller than 1. So you get some upper bound smaller than 3. And so there's always exists some incompatibilities in these examples. Right? Then we perform some kind of experiments on powerful cloud quantum computing, which is a cloud quantum computing provided by the Beijing Quantum Academy. So we're choosing one optimal measurement. To implement this optimal measurement, you need to design some gates, which consist of 3 C0 gates, which is kind of complicated. But we also compare with some simple but non-optimal gates or measurement, which is often used to measuring these parameters. But although this kind of complicated, which consists of multiple C0 gates, the performance of the optimal measurement is still better than the non-optimal but simple measurements. Right? These are kind of these are some. The line is the theoretical bound, and the dots are this simulated simulations, and this the triangles are the experimental data on this cloud quantum computing. Right? Simulated. So the second example is just 2 parameter quantum estimations, and I forgot to mention that. So for 2 parameters, our bound actually can recover this GM bound with on qubits. So this example on qubits with 2 parameters, the GM bound is just smaller than 1. Now, in this example, we want to show that the flexibility of design of the optimal measurement. As we just mentioned, the optimal measurement to achieve our bound is infinite, it's not unique. So there's some flexibilities. So we compare this the optimized measurement according to the settings with another optimal measurement, which has not been optimized according to the settings. You can see that the optimized measurement has less C0 gates, so naturally it performs better than this optimal measurement, but does not further optimized according to the physical settings. They are both optimal theoretically. So we also apply this our trade-off relations to quantum radars. So in quantum radars, so basically the basic setting we study is that you have some entangled photons, and then sending one single photons to the object, which will reflect back. Then you take some collective measurement of the two photons. Right? So I'm not going to go through the details of this states. I'm just going to mention that there's a quantity in these states, kappa, which quantifies the correlations between these two photons. When kappa equal to 0, the two photons are separated, so there's no entanglement. When kappa go to 1, then it's a complete perfect entanglement. But the perfect entanglement in practice is not realizable. So the quantity we are interested in to measure is the range and the velocity of the object. And the range is estimated through the flight of time. So you're detecting the signal will go to the object, then do it reflecting back. This time is corresponding to the range, right? And the velocity is estimated through the frequency. Because when the object is flying with certain velocities, the signals, frequency of the signals will be shifted due to the Doppler shift. By detecting the shift of the frequencies, you can estimating the velocities. So there's two parameters here, and the range and the velocities, or the time and the frequency in these photons. Right? Since we have the states, so I should also mention that here we are assuming there's no noises. We're just interested in the ultimate precisions. So they're not considering any noise here. So the states are also considering the object as some kind of perfect mirrors. So the states is remain pure. Right? So since we have the states, so then you can calculating the classical quantum Fisher machines, and which is given by here. If you just applying the quantum Kramer bound, and then you can get the lower bound for the multiplication of this variance of t and omegas, right? Which actually this bound is actually obtained by in these papers. So directly applying the quantum Kramer bound, but that's actually this bound is actually in general not achievable due to the incompatibilities. For example, when at kappa equal to 0, when these two photons are separable, it violates these conditions. Becomes bigger than 1/2. The right hand side, when kappa equal to 0, becomes 1/2. And this actually violates the Arthur-Kelly relations, right? Which is this is at least the right hand side is at least 1, right? But this inconsistency is mainly due to the incompatibility, right? Because that's because the this relation obtained from this quantum Kramer bound is not tight, right? Because this quantum Kramer bound is not achievable. Consistency is mainly due to the incompatibility. Again, I'm going to skip all the derivations. Basically, if you substitute into our relations, then the classical Fisher machine has to satisfy this upper bound, right? And this can be transformed into this lower bound for this multiplication of the time and the frequencies, which give you these quantities. Now, if you substitute k equal to 0, this gives you the right Arthur-Kelly relations. And when kappa equal to arbitrary quantities, so for arbitrary entanglement, this gives you an achievable lower bound. Right? We can actually constructing optimal measurement to satellite this lower bound. And this gives you the ultimate performance of quantum radars with entangled by photon states with the arbitrary amount of entanglement. So compare this our relations with the relation obtained from the quantum Clammer bound. We can see that the gap between our relation and the quantum Clammer bound actually decreases when k increases. Right? So this entanglement not only improves the precisions, but also reduce the incompatibilities. Right? Right, so this is the measurement incompatibilities. I'm going to briefly talk about the probe incompatibilities. So the probe incompatibility basically just means that the optimal probable states to estimating different parameters can be different. So there's not a single probable states that are optimal for the estimation of all parameters. So you also need to make some trade-off among the choice of the probable states. So for example, if we want to measuring vector magnetic fields, we want to measuring all the three components of a magnetic fields. Right? It is well known that if the magnetic field is pointing to the z direction, then the optimal probable states is just the GH states. And if the magnetic field is pointing the x direction, and that's the GH states along the x directions, which just plus plus with the minus minus superpositions, right? So, and it's easier to calculate if there's only one component. So suppose the vector field is just only have one component, either B3 or either B2 or B1. Then you prepare the GH states and the minimum variance for a single parameter is given by this low bound, right? So for each parameters, these all give you the lowest bound you can achieve, right? But for the estimation of all three parameters, if you sum these three bounds together, you will get a trivial bound. But in general, this trivial bound is not achievable due to the probe incompatibilities, because the achievability of this each lower bound, you need to using a different probable states. Right? Again, we skip all the optimization procedures. Just tell you that, and if you're making a trade-off among the optimal probable states, the minimum summation of the variance you can achieve actually equal to these quantities, which is indeed larger than this trivial bound we obtain. I should also mention that the optimizations can not only perform for these equal summations, but can be performed with arbitrary weights. You can also perform these optimizations, get some minimum bounds. Right? And the optimal probable state to achieve this minimum bound can also be constructed. But I'm going to skip this construction of the optimal probable states. Essentially, this is just some kind of linear combinations of the three different types of the GH states. But you need to carefully choosing the coefficients. Construction of the optimal probable states. Right. Essentially, this is just so basically I talk about this how to perform the optimal precisions for the estimation of single parameters. Then talk about this analytical bounds on the measurement incompatibilities, and give you some special case of the probe incompatibilities. And there are many open problems in the incompatibilities. Of course, there's already some numerical approaches for these problems. For example, Hayashi and Ouyang developed some conical programming numerical tools on this incompatibility problems which are related, at least. Right. So a lot of work is done by my PhD students, Wang Lingna, which is now a postdoc in my group, and Chen Hongzhen, which is now assistant professor at the Shenzhen University. And that's a single parameter case is collaborated with Yang Yuxiang in Hong Kong University. And right, thank you.
Thank you very much. Thank you very much. Are there any questions, comments?
Sorry, so I have several comments on the question. So could you show me what is your Cramér bound?
Cramér bound?
Yes. But multi-parameter case, the definition of Cramér is not unique. What did you define?
This Cramér bound?
This is one parameter case. This is trivial. So I'm asking, how did you define the Cramér bound in the multi-parameter case?
Multiple parameter. Yeah, I didn't write it down, but yeah, so it says you can generalize this a single quantum Cramér bound quantum Fission matrix to multiple quantum Fission matrix.
No, this is not so trivial. So there are so many developments to define multi-parameter case of the Cramér bound. There are so many ways.
Oh,
Not
right.
trivial,
Here
not trivial. There are so many methods.
Here I'm right. Right. Here I'm using the SLD.
Not only SLD. So then you need to take some trace. Simply you take trace.
I didn't hear clearly. Can you repeat?
So this is usually it is impossible to make a simultaneous minimization of the component. Now you are considering a covariance, but there are so many components. So first diagonal component and second diagonal component. So it is impossible to minimize both components, both diagonal components. First component, the second component. Here is trade-off.
Right.
So that's problem. Usually we make the weighted sum. So weighted sum is a very usual method. So then you make some minimize for the that trace of the covariance. So in that case, you have some lower bound. So you in that case, you can take a trace of the SLD Fisher information matrix, inverse of SLD Fisher information matrix. This is one method, but there are so many methods. So you need to review the existing method. So in the case of multi-parameter case, the problem is very complicated, but you completely ignored some existing method. There are so many methods already studied more than 20 years ago.
All right. Yeah. So there's many methods like generalize single parameter quantum estimation to multiple quantum parameter machines.
Yes, so many research exists, and there are so many versions of the Cramér bound. So there are so many versions. So this kind of discussion is quite naive, so not so good. You need to more carefully define the multi-parameter version of Cramér bound.
That's a good suggestion. Yeah. Thank you.
And the second one is please show me the Ozawa's one.
Which one?
Ozawa's inequality. Ozawa.
Ozawa. Okay.
Yes.
That's a good suggestion. Yeah. Thank you.
And the second one is please show me the Ozawa's one.
This one. Which one?
Not yet. Ozawa. Ozawa's one. Next.
This is Ozawa.
But I cannot see this one. Yes, this one, yes. So this is something misleading. So Ozawa completely ignored Nagaoka's contribution. Nagaoka already considered this one. But Oda completely ignore this one. And Nagao already studied two-parameter case with that mixed state case. And also, I also consider that one almost same time as Ozawa.
Oh, okay. Okay. Yeah, I should add those references.
Recently, somehow you know that Nagaoka Hayashi bound, but originally that bound come from the Nagaoka's one. So maybe you should read some paper about that Nagaoka Hayashi bound paper. So this is not written by me, some other guy. So I cannot remember. So maybe Nature Partner Journal of Quantum Information. In that paper, they review the result of Nagaoka's one. So in that case, firstly, that paper, firstly, we minimize the optimize some measurement. So firstly, we pick some observable. So, but in that case, there are some trade-off. So because X and Y cannot be measured simultaneously, but firstly, we fix some observable. So then we make some lower bound. In that case, we use that kind of quantity. So C12, this is maybe you should take trace, I think. You should take trace. You did not take trace, C12. This is still operator, I think. No, you take trace, okay, one. So, yes, okay. This is trace norm. Okay, this is trace norm.
Yes, this is trace norm.
Trace norm. Okay, I understand. Trace norm. So, in that method, we use this one. So, Ozawa's one, he take only the trace and absolute value, Ozawa. But we can take the trace norm here. So this is a generalization for the mixed state case.
Okay. Okay, thank you.
Okay. Other questions, comments? Okay. If not, let's thank the speaker again. Thank you very much.
Thank you.
So let's have a 10 minutes break. If not, let's thank the speaker again. Thank you very much. So let's have a 10 minutes break.
Mm. どうしようかね。それから、
Yeah, Hayashi Sensei, we can see your slide.
I think you can see our slide, I think.
Yes.
So now I close the
Yeah, it's
other,
okay. Okay.
other file. So because I need to avoid that trouble.
いや、まだバッテリーは8割ぐらい、8割以上。
全然じゃあ、あれですね。そんなに心配
一個は向こうに。
じゃあ、
多分。
Okay. Hold on. Sorry, I forget one comment. So, because in the case of that kind of SU2, all three directions can be measured simultaneously. This is possible. If we employ the entangled state, if you input the entangled state, X and Y and Z is commutative. やばい。まさか切っちゃった私。 やばい。難しいな。
Okay, let's resume the session. The last speaker of today is Masahito Hayashi. The title of his talk is Asymptotic Dimensional Analysis on Unitary Representation and its application to measuring quantum relative entropy. So please start.
Okay, thank you for introducing me. So today I talk about this topic, but this part composed of two parts. First part is asymptotic dimension analysis on unitary representation. So this is the first part. And the second part is estimation of relative entropy. So second part, so firstly we discuss this one. This part is completely mathematical, so completely mathematical topic. So you don't need to any knowledge about quantum information. You need some knowledge about group representation theory. And the second part is its application to the estimation of relative entropy. This is somehow related to the CC1 talk. After the second talk considering the estimation of the various kind of entropy, fundamental entropy and linear entropy in the quantum setting. So our case considering the estimation of relative entropy, but these cases include some estimation of the fundamental entropy as a special case in some sense. So, firstly, I discuss representation theory. So, as you know, H is some Hilbert space, and that dimension should be D. And this one can be converted to this way. This is a unitary representation. So V part is a representation of the unitary part, and U is unitary part. SUD part, and V is a part on the permutation group. So the representation can be decomposed this way, and that kind of representation described by using the Young tableau in this way. So we often use D1 is the largest and D2 is the second largest, but now we consider this order increasing order, not decreasing order. This is some notation related to some of our mathematics. So we want to use this notation, and we impose this. N is the number of tensor products, and Y is this one is Young tableau. So this one must be greater than 0, and this is positive number, and the summation is this number. So this is the set of that kind of integers. So this kind of tensor product space can be decomposed this way. So now we want to discuss this number. So this is the unitary part, and the unitary part take some direct some product and its dimension. We want to discuss this number. And sorry, this is d lambda. So that kind of dimension. So each dimension, u lambda should be write down d lambda, and we want to calculate its sum. This is d lambda. So of course, it is well known that this one is upper bounded by this one, and each lambda we have this dimension. This one is wild dimension formula. This is very famous one. So this one is upper bound this one. So the main part is that we want to calculate this number, or we want to discuss this number when D is very large and S and also very large. So sometimes in quantum information, some information theory guy consider the case D is fixed and N only N increase. This case is very easy and we have this behavior. So the dimension only increase about the polynomial for N. So if you take the logarithm of D, so the lambda, so this one is order of log N. Somehow not so difficult. So that we have this one. But some computer science person and also second speaker talk Chi in his case, he considered the case when D and N increase simultaneously. So in that case, what happened? We want to discuss this situation. D and N increase simultaneously. So in that case, how about the behavior of this? This is today's problem. This is very mathematical problem. So now we consider the case N equal to this polynomial, but this is polynomial and D plus T, and T is some real number, but sometimes negative, sometimes zero, and sometimes positive. So this one includes several cases. So then, so we want to calculate this one. So the final purpose is that we need to calculate this sum, but the number of this sum is not so many. So only it is enough to consider maximum case, maximum D lambda. So it is enough to consider maximum D lambda, but we need to calculate this number, this product. As you know, this one can be changed to this one. So you can change log and product, but in that case, this one becomes sum. So then this sum can be converted to this one. And basically, this sum, number of this sum is the order of D square. And mainly this term, this is, sorry, I had a mistake. This is log. So log of 1 plus this guy is upper bounded by log n. Log n, because the summation of this guy is n. So then n is the polynomial of this guy. So then this is essentially order of log d. So then now we are considering that we have this number of summation d square, and each component is upper bounded by log d. So then this quantity is upper bound this one. But it is not so clear this upper bound is so tight or not. Some, of course, the maximum guy has some behave with this order, but some guy has not so large. So then a lower bound, we have this order to D square. So then we can easily find that this is lower bound, this is upper bound. So we want to get the more exact analysis, order analysis of this one. So then we have this case, and this is our result. This is our result. If this t is smaller than 0 or equal to 0, so in that case, this guy. But if t is strictly larger than 0, so in that case, log d. So this means that the depending on t, we have this lower bound equal, and depending on t is strictly positive. So in that case, we have equality here. So depending on t, we have a different equality for these two inequality. This is the first result in this talk. So we want to explain how to evaluate this one. So as you know, we already gave this calculation. And later we convert this. This looks trivial, but why we need to make this strange way? So because in the second step, we have this inequality. So why we have this inequality? This guy equal to this one. Because now we consider some probability distribution. So now we consider, please ignore this one, only we have this one. In that case, this one can be considered as a uniform distribution on I equal 1 to d minus 1. D minus L, sorry, this is d minus L. So we have some distribution here, and we have this some random variable. So this is random variable, and this is distribution, and we take its average here. So in that case, log 1 minus plus something, this guy is concave function. So then concave function has some inequality by applying the Jensen inequality. So if you move to this average inside of this function, so then we have take average first, so then you take this concave function, then we have this inequality. So this is the Jensen inequality. So this is inequality is very essential. So then we have this inequality, and we calculate this one. And so of course we can ignore this one because this is somehow to get upper bound. You can ignore this one, and we have this one. And taking this sum, all of this sum equal to n. So this means that we have not all sum. So then we have an upper bound of n, upper bound n. So then you can calculate this one. Now we consider maximum case. So t equals 0 case. We have this one. So then we can calculate this one. So we divide by d. So then we have this one. Finally, you take the in order to take that dependence of d square, so we divide by d square this one. So then this upper bound is this guy, and but now we found that this one can be changed to the integral because this one is yes, this one is 1 over d. Essentially, this is 1 over d, and d over L replaced by x. So then we have this integral, and we have this integral can be changed to in this way, so this way. And then finally this one can be upper bounded. But you can directly calculate this integral. Also, this integral is a finite value, so not infinity. So you can easily directly evaluate this one. This is also high school mathematics, but somehow I'm not so familiar with this calculation. So then we need to calculate this one. So, but this part is only d square. So then this one part is more important. So anyway, so now we consider d is smaller than t is this one. So now we consider this case, and t is at most positive. So the maximum case, even in the maximum case, we have this term should be constant. So then we have this one. T equals 0 case is this constant, and if this one is smaller, but still we have a lower bound, this one in the previous discussion. So then we have this one. So now we consider opposite case. So if t is greater than 0, strictly greater than 0, this one is t is positive, strictly positive. So in that case, we can choose lambda j behave this one. This is possible. This kind of choice is possible, some order. So 1 plus strictly t. So in that case, we can calculate this quantity, and in this way. So then finally, we can calculate this one, and then finally, essentially, we obtain this quantity. So in that case, what I want to say is that log d and order t, we have order t, this one. Finally, we have this t. This is positive, strictly positive. So then, what we have this one. So the number of summation is d square, and each term is lower bounded by log d. So then we have this lower bound. This is log d. So then what we obtain? we can back this one. So previously we mentioned that this is upper bound and this is lower bound. So, but yes, so depending on the value of t, we have this one and this one. So to calculate this one, we need something like about the relationship with probability theory method, information theoretical method. And second, now we using that result, we can discuss the estimation theory of this one. So we need to calculate relative entropy. This one, relative entropy is that so d rho sigma is trace of rho and log sigma minus trace rho log rho minus log sigma. Then we need to stop here. We need to stop. So then we have a relative entropy d. If we stop here, this guy is relative entropy, but later we need to consider some variance, so later we need to use this. So we want to estimate this quantity, but here we assume that we exactly know the form of this density matrix sigma. We know sigma, but we don't know this rho. We don't know rho. But in that case, we need to make some measurement. So we need to make some measurement and we need to estimate this one. So instead of the mathematical form rho, we have n copy of this state. So we have some n system, and each system has density matrix rho and total density matrix rho tensor n. So we have some system whose state is this form. So then using this one, we want to estimate the form rho. So this one is almost same as this is sample complexity problem. So this is quite a simple problem. So, but in that case, there is somehow quite a difficult problem. This is one parameter estimation. We need to estimate this, but the parameter is not so simple because we don't have our case is not one parameter. We have so many parameters. So we don't know the form of density matrix. So then we have so many parameters beyond this relative entropy. So in that case, quite annoying to estimate the other parameters. But in that situation, there is a quantum estimation theory for the one parameter case with so many nuisance parameters. Nuisance parameter means that we don't know that parameter, but we don't need to estimate other parameters, nuisance parameters. Our interest only on the one parameter to describe density relative entropy. So in that case, somehow there is some estimation theory. If the system size is fixed and the density matrix number of n only increase, so in that simple situation, what we have in that case, there is a parameter bound, and in that case, this V is very important. This one gives us that kind of Fisher information, inverse of Fisher information. So this one gives a parameter bound. So, but that kind of parameter bound is not so simple. So, because we have a nuisance parameter, so in that case, we need to calculate projected Fisher information. So, projected Fisher information and inverse of projected Fisher information is equal to this guy. So then there is some known result. So that mean square, optimum case, non-square, mean square behave as this one. But Fisher information, but we cannot perfectly tolerate this theorem. There is so many conditions. So I don't talk somehow problem. So he did not care about that problem. So only calculation of Fisher information is not good. There is a very dangerous problem. So because the equality does not hold in general. So in order to show that equality, we need to mention so many kind of conditions. So this one is very, very complicated problem. So if we have any copy of same system and the system size is fixed and n go to infinity, so in that case, maybe we can say this one. But still, we need some regularity conditions. So saying with all regularity conditions is very annoying problem. So anyway, so we have this order. When this system is fixed and only number of n increase, then we can say this one. However, in the computer science, people never trust this situation because we need to consider that the system size also increase. So in that case, we cannot employ that result. So then their problem is very, very complicated. So we cannot trust this result. We cannot trust this result. So this is only some result only when the case the system size fixed. Then we have to consider the good measurement. We remember the shear duality. So we have this decomposition and state and density matrix written as this form. This is complete mixed state on the system V. So because this part is essentially has some identity form, but we want to choose this density matrix. The traces should be 1. So we write down this way. So in that case, our information has this one. Of course, now we assume that we know the form sigma, so we don't need to estimate this one, but we need to write down this form here. And the state part is this one. We don't know that this is rho lambda. We need to estimate this, right? So in that case, what we have, so this we want to consider n times the density matrix, this one, and this one equal to n copy of relative entropy. And that relative entropy can be converted this way by using this form. So now we need to estimate this one, but in that case, it is enough to estimate this one. So how to estimate this one? So firstly, we choose the orthogonal basis on the system U, diagonalize this one. So this one is eigenvector of this matrix. So in that case, now we make normalization here, but now for this part we don't need to make normalization. Now we make normalization here. So in that case, this quantity is almost close to this one. We can show this one, and the difference is quite small. This is upper bound. This is smaller than 0, and this guy is dimension of the system d lambda. So this shows that the difference between this guy and this guy is quite small, upper bounded by log d lambda. The difference is log d lambda. So using this fact, we make some estimate of the density matrix in the following way. So we define the P of M element positive operator in this way, and we make this one. And we write down this value depending on lambda and j, because firstly we make decomposition for lambda, later we make measurement of the basis of j. So then we calculate this quantity and this one. This is depend on sigma, and we need to we make this measurement when the state is this guy. So then we have this output distribution. So here we need to write down rho and sigma because this is depend on rho, but also the choice of the basis depends on sigma. So then we write down rho and sigma here. So depending on rho and sigma, we have one distribution over the with respect to lambda and j in this way. So in this case, what we have, so mean square error over the dot estimate. So because this is an estimate and this is true value, and we take its average, the difference of square error over average of this one. This is a distribution, and this is square error. This is estimate, and this is true value. We take its average here. So in that case, this mean square error is upper bounded by in this way. So this is upper bound. This is our result. So this means that and we have this parameter, this value here. If this guy is 0, so then this mean square equal to the Kramerov bound. But unfortunately, you cannot ignore this contribution. So we need to consider when we can ignore this one. So now we remember that previous result. So in the first part, we already shown that n equal to this case. In that case, we have this behavior. So this case, we have 3 cases. So this is not so difficult. So if that t is strictly greater than 2, so in that case, this part is relatively negligible compared with this part. this term becomes the leading term, and this part is the negligent part. So then we have this evaluation when t is strictly greater than 2. And if t between the 0 and 2, in that case, this part becomes a leading term, and that behavior can be described by this way. And t is smaller than 0, so in that case, this one is this one. So this means that this one goes to 0 in some order. But there is one problem. If t equals to 0, this is constant. So in that case, what happens? We need more careful discussion in the case of t equals 0. So now we consider t equals 0. What happens? In that case, we assume some condition about this guy. Otherwise, some problem. So because this behavior of v is also quite important. So, but still, if behavior of v behave in that case, so in that case, this additional error term behave this one, and then our mean square error are bounded this one. So in that case, this term is not so serious. So then we have this upper bound. So this means that if c increases so enough, so in that case, this are bounded by epsilon. Yes, if c is greater than this one, then this mean square is smaller than epsilon. So this means that the sample complexity is n square. No. Sample complexity is yes. だからどうするんだっけ。sample complexity is yes, n equals to d square. Yes, n equals to d square, then we can achieve this one. N equals to this one, then we have this one. Sample complexity. Now we want to compare with, of course, the case of the estimation fundamental. In that case, this is identity. If we choose low sigma is identity, so then yes. So in that case, this is identity. So in that case, this guy equal to Von-Neumann entropy. So then the Von-Neumann entropy is included in our analysis. So there is so many existence methods. Most famous existence is full tomography. So full tomography is the following. So we want to estimate the form of the density metric perfectly, but in that case, the threshold between the true one and estimate should be smaller than epsilon. In that case, how many copies of the unknown state? In that case, we need this number of copies. This is the existence result of the sample complexity. But now we want to realize this condition. This is epsilon prime, and our estimate is this guy, and this one is true value. But now we allow the sigma d has a very small eigenvalue. If this one has 0 eigenvalue, so in that case, relative entropy become infinity. So this is we need to avoid that case. But still, we allow the very, very exponentially small eigenvalue. So in that case, under this condition, in order to achieve this condition, this is more complicated because the difference is upper bounded by this, right? So then to achieve this condition, we need to satisfy this condition for our estimate. So this means that conventional use of the full tomography requires that this number of copies, D and 4, this one. This is extremely many, so this is very serious problem. So our method is only this square, but if we simply use the full tomography, the sample complexity becomes 2 power 4. So then we have a very significant improvement over the full tomography. But in the case of Von-Neumann entropy case, the comparison between the full tomography and specific tomography method, the difference is quite small. In that case, d square over log d something, log d, so log d added here, so log d added here. So then the difference is not so large. So then this is the conclusion. So we have derived the asymptotic behavior of dimension insurance duality. This is the mathematics part. So then using this one, we have discussed estimation of relative entropy. And we also derive the sample compression of the upper bound of this problem. Our method improve the conventional fluid tomography in this method, in this problem. So this is reference, and this one is second speaker's talk. So thank you very much.
Thank you very much. So, are there any questions or comments? We have plenty of time. So please. Mike. So there's a question on Nagoya side.
Can you hear me?
Yeah.
I have a question.
Oh, excuse me.
Excuse me.
So please, online participant. So question from Dongyan.
Okay,
Please.
thank you. So my question is that does your approach work for the quantum linear divergence? Because here you use the approach to estimate the linear relative entropy. But in general,
Maybe possible, but not so easy. So you need to make more complicated calculation. So in any case, I don't know. You can consider that problem. So, but any entropy case, どうしたっけなThis method maybe works well with the case of sandwich Renyi case. But Test-Renyi entropy, this method does not work with Test-Renyi method, Test-Renyi divergence. Sandwich cases works well. So because we make this kind of measurement, even though we make this measurement, after the measurement of the this divergence does not change. So this is some good point. So, but in the case of PET divergence, measurement of Renyi divergence does not converge to the PET divergence, but measurement of Renyi divergence equal to the convergence to the convergence to the sandwich Renyi divergence, as you know. Okay, so then maybe possible. So
okay, okay, thanks. So another question is that can the rho, so in your case, the rho is the unknown state and sigma is known. Could you use the approach to estimate? I mean, when the rho and sigma is exchanged, but of course you have to promise that the unknown rho is, for example, have the full rank.
Because quite difficult. So because of course if sigma is not full rank, so usually real entropy become infinity. So the problem setting does not make sense. So we need to make that kind of assumption. This is quite reasonable assumption. And second, so if we change rho and sigma, the problem is very, very difficult, as you know. Because Relative entropy is quite sensitive to destroying the second state. So if you destroy the second state, second input state, relative entropy is maybe drastically changed. So this is not good. The same method does not work.
Okay, but
Okay.
I mean, okay, thanks. Let's talk
Okay.
about that later. Okay, thanks.
So there is another question from Nagoya.
Thank you for a nice talk. So my first question was the same as Mr. Donyan. So the second question is, what is the intuition behind the parameter T? Could you explain more on it?
This is parameter T is this one. So now we consider relationship with N and D. So in the computer science, people want to consider that case N and D is increased simultaneously. Not this case. No, this case is very easy. So now I change this case. So in that case, how to make the relation? So I make this relation. So in that case, we want to discuss the behavior of D lambda, maximum case of D lambda. So the solution is this one. But of course, if you increase this one, we have a lower bound, upper bound in this way. So then we have which one becomes true equality. That answer depends on T. This is my result.
I see. So in that case, N is a kind of minimal number of necessary samples, and T is a parameter which as small as you want to make as small as possible, so that N is kind of small compared to D.
But of course, in the case of problem, finally we obtain this result. So this one must be go to 0. In that case, yes, this one does not go to 0. No. This one does not go to 0. This one go to this is go to 0, and this one does not go to 0.
Okay, I see.
But still T equals 0. This one can be bounded by any epsilon. So then the sample complexity corresponds to T equals 0.
Oh, I see.
But I want to hear, I have some questions. So that kind of analysis existing or not in the area of pure mathematics? Because this is a purely mathematics problem. People already consider behavior of this dimension. I want to hear a mathematics person.
Any mathematics person? Yeah.
But I also have similar question to Kato-san. I mean, I understand D is a dimension of Hilbert space, and N is a number of copies, right?
Yes.
But why you assume such a relation between N and D, something like that, N equal order D to the 2 plus L, how they are related?
Now this is only an arbitrary choice. So this is polynomial case. If we have some polynomial relation, we have this order, I think.
Basically, they are independent, no?
Independent case is quite difficult to evaluate. So then we want to make this one. Because we want to consider some relationship D and N. Otherwise, we cannot discuss that asymptotic behavior. It is quite difficult to consider two parameters independently. This is almost impossible.
Yeah.
So then we assume that some polynomial relationship. So as a typical case, we consider this one.
And that motivation comes from the estimation of relative entropy.
Yes.
Okay,
but in the pure mathematics area, people, I think, consider the maximum of this behavior of this dimension, I think. Or nobody consider that problem. Of course, finite case, finite means that d fixed and only n increase. So usually this upper bound is very nice because this one gives us some log d equal to log n. So we have this evaluation. This is very usual, but this is too easy. So then I consider more difficult case. Evaluation of this term is not so trivial, I think. Depends on the order on parameter t, which that equal true equality changed. True equality depending on the parameter t. So I want to share the opinion of mathematics person. How about Yanagida-san? So do you know that's the answer? Or mathematical person never consider that problem?
I have never considered such problem.
Because mathematics person never consider order estimate. But of course, if we fix d and only n increase, that problem is very easy. So then that one is the log of d is only the log n. So in some sense, this is negligible. So because total dimension increase the exponential for n. So this part is not so easy. So this is negligible. But some situation, d and n is increased simultaneously. So in that case, the problem is very difficult. So then we need to consider that problem. So this is more difficult problem, I think. Of course, even though in both cases we have a lower bound, upper bound in this way. So, if n and d independently, still we have a lower bound, upper bound. N and d increase independently. So still we have this upper bound, lower bound, I think. Maybe here is log n something, log n something. So. But which inequality becomes true equality? So this is depend on that kind of relation. So to get the tight evaluation, we need this kind of some exact relation between n and d.
Okay. Other questions? Comments? So if not, let's thank the speaker again. Thank you very much. So this is the end of today's program. So tomorrow we shall meet again at 9:30 in China and 10:30 in Japan. Okay, see you tomorrow.
See you.